Alright, so this is the first video in what I hope is a series on building a bytecode VM and a compiler for that, or assembler, and then a compiler for a high-level language that will target that VM. My goal with this is to keep it all very small and very simple. One of the frustrations I've had as I'm delving into building my own language is that a lot of the educational resources out there are very complicated. So you might get something where you get a very simple interpreter for arithmetic expressions or something like that, and then you go deep into parsing theory and optimizations and even just simple things like code generation are difficult sometimes to pull out of a lot of popular resources. And I was actually very surprised how hard it is to find information about this topic. I have a project where I need to do this, and I've been researching it so much I decided I'm going to make the video that I wish I had found to start with. So my goals with this are to keep it very simple. I'm not necessarily making a highly optimized VM or compiler. And also, I'm not really trying to be very robust. I don't need to have really elaborate error messages. I don't have to have a lot of error checking and other things. The goal is to learn, build, and illustrate what it really takes to make a language, a working programming language. One of my commitments too is that I'm not going to give up after I have some very simple parser and evaluator. I really want this to be a full-scale general-purpose language. Might not be humongous, but should be a complete one so that we can see through the process and in the final product that it's got all the basic pieces in it and could be expanded or enhanced into other areas. To start with, I'm just going to write a small bytecode VM in C. This will be the first stage. Today's goal really is just to get something that can run bytecode. It won't be able to do very much, and one of the things I've been thinking about too here is that as far as what this is going to do eventually, I might be growing it and changing a little bit over time. So I'm going to do all the code live. I do have some notes. I'm cheating a little bit because I don't want to waste time Googling for something that I should otherwise just be able to type out. So bear in mind that all of the code that goes into this final VM compiler and assembler is going to be produced during the videos, though I am looking to the side to make sure that I spell stuff correctly and don't waste too much time on the video. So just to start with, we'll do a basic C program. Of course, that's essentially hello world without printing hello world. But we have to think about what a programming language is. And in this case, I'm really starting at the bytecode VM level. The bytecode VM goal is to create a little abstract machine that my language can target so that I don't have to worry about the substantial complexity of targeting machine code on my actual hardware CPU. Most programming languages now either do this or operate with a back-end compiler like LLVM or something along those lines that allows you to kind of ignore the vast complexity of the hardware platform. So most of the scripting languages, if you're looking at Ruby or Python or something like that, you're going to see that underneath there's a little bytecode compiler. Java is obviously one of the big examples of this. One of the daunting issues with trying to understand how to create a bytecode VM is that a lot of the big VMs are really, really big. They have lots of optimizations. They're ginormous code bases underneath. Very, very difficult to understand how they work. There's some examples I've seen, some very pedagogical examples, where they end up being kind of so simplified you wouldn't really even use them. I'm trying to target a little bit better than that, but again, I'm not really going for extremely optimized product here. So one of the most important things in any language is that a language has data, and it has data of different types. I'm going to start off with just how my VM is going to represent those types. If we were compiling to machine code, we would be thinking about how a character is 1 byte and an integer is 4 bytes, 32 bits, right? And we might have a lot of difficult type checking, and code generation might be difficult if we're going to just let all of that stuff be represented in the process of taking my high-level language to the low level. But if I build my bytecode VM so that it's type aware, that abstracts some of that away from the needs of my higher level language. It's one of the advantages of having a bytecode VM. So the first thing we really need is some way to express some fundamental data object in the language. So I'm just going to do that with a regular struct. In this case, I'm just going to call anything in my language is going to be an object. I'm not talking about an object-oriented programming type of object. This isn't like C++ or Java object. But for now, we're just going to call this thing an object. So in our VM, we're going to label each object. Each one is going to carry around a little tag that says what type it is. This way, the bytecode VM, and then maybe later if we expose some of this information to the higher level language, depending on how I build it, this information can be used to make decisions about manipulating different parts, different pieces of data sitting on the stack. So I could do this with some flags and have some other stuff. We might end up with some other basic information, metadata about data objects, but for now all I need to know is what type of data each one is. And then in an object we have to store the actual value that is represented by the object, and this is one of those rare cases where a union is actually useful. I remember a long time ago I had read about unions and I thought, man, I don't think I'm ever going to find a use for a union. And this actually is one of those perfect cases, because depending on the value of this type slot in the struct, it'll determine how C will interpret how the data is stored in the rest of the struct. So we can say we have a type, and every object is going to have a type, but depending on that type, then the object may have, for example, a U8 field. So a U8 field is going to be the value for, say, a character or an unsigned integer that's 1 byte. By the same token, if we say, well, we're going to have another value, another type, which might be a signed byte, well, that's going to be an I8. And the union, in case you're not familiar with how unions work in C, this doesn't mean that every object has both of these fields. It means the same space is occupied or can be referenced as these values. So depending on the type, I'll be able to take action using these different names, and that allows the C type system to understand and appropriately address this information in these objects. Hopefully that makes any sense at all. I don't suppose it really did make too much, but anyway, suffice it to say that that gets us a basic way to represent objects. Eventually we'll have more in here. For example, almost certainly we'll need pointers. So for example, I might have a void pointer, and so that way an object may represent a pointer to some place in memory. And then eventually we'll probably have something in here to represent some sort of collection. So maybe it's going to be a vector or an array or something like that. I don't want to have too many spoilers in here, and I'm not entirely sure how that's going to look eventually anyway. So for now, we're just going to have a very basic concept of numbers of different sizes and signedness, and maybe a pointer. So from here, now we can create ourselves a little makefile. Not there. Where am I storing this? Oh, series. So to compile this thing, you just want to default. So far, we only care about vm.c. So make, of course, we got some angriness here. Let's go back. I forgot to say, because I've become a fan of standard.h. Since from the dawn of C, we've got characters and shorts and longs and ints and things, and the sizes of those and other things aren't just explicit in the type name. So I decided I'm going to use this design for now. Of course, VM doesn't do anything, and it just returns a successful value, but this at least tells me I spelled it all correctly. So in addition to having objects, we need a place for the VM to store data. There are usually a couple different types of VMs that people build. If you look at the JVM for Java, it's what's called a stack machine, and that means that fundamentally all of the basic instructions that execute within the virtual machine operate on a stack. And then you might have other designs. I'm not sure right now offhand. For example, I think the CLR for .NET might be a register machine. Not sure, I'd have to look it up to be confident. But register machines occur also, which are patterned more after what we see in hardware, where you might have a more complex state at any given time. There's a list of registers or places where you can store values, and then your instructions are going to operate on those registers. There are pros and cons for each one. Frankly, I don't care too much one way or the other, except that stack machines are a little more common, and because my eventual high-level language is probably going to be more compatible with it, that'll become more apparent in the future, I'm going to go with a stack machine. So we need some sort of stack data structure, some way to represent a stack. And in doing some of my sketches for this in other contexts, I've found that the more abstractly I define this kind of stuff, the better. I don't want to have the specific guts of manipulating the stack scattered all over my code, because if I do want to change how it operates, it gets very difficult to manage it. So we'll do at least a kind of essential design for an abstract stack data type. So this we'll just call a stack, and we have a top. So this is going to be just the next index in the stack. We'll start the stack at 0, so the first element on the stack is going to be element 0, and then top is going to point to the next location where we're going to put an object on the stack. Just very simply. Of course, the stack has a limited size. We want to make sure that we don't exceed that. So it might be a long time before I actually put that kind of error checking in here. And then we have some array of objects. I do want stacks to be able to be defined of different sizes, because we might have, say we'll have a 32 element stack for local variables, and maybe we'll have a 1024 element stack for return pointers or something. Who knows where we're going to go with this, but we'll keep it generic. And that means we need something like a constructor to create a new stack. So we'll do it something like this. All we need to know creating a stack is that it's going to have some size. And I'm doing this one by value. It doesn't really matter how I do this. I could also dynamically allocate it, but do the casting just so C is happy. Right, so we're going to create a stack, and it's going to start off with pointing at the 0th element, because that means it's an empty stack if that's pointing at 0. And then the size, of course, is how we define it. And I'm just allocating space for however many objects we're indicating there. So stack contents are stored on the heap. And let's see, so there are canonically two things that you can do with a stack. So you can do a push, where you take a stack and then you take some object you're going to push onto it. And then there's also a pop, where you take some stack and you're just going to take the top item off. And then I'm going to extend it, the kind of conventional ability to peek at the top of the stack. That way I can look at that top object but not necessarily remove it. It's not canonically part of a stack, but may as well be for now. So for pushing something onto a stack, all we really have to do is store the object, and all of the objects are passed by value. And notice that when we look at the definition of an object, none of this is dynamically allocated. So this is a fixed size, which means everything that goes into there to an object that's going to appear on the stack fits in a pretty small space. I think currently this takes 8 bytes of memory for each object, depending on how it gets packed. So we want to store something on the next location in the stack, and except we also want to increment that. So we put an object on the stack, we assign it its value to the next location, and then increment that location. And actually, I don't want to return a stack, I want to return an int. And actually, these need to return objects, don't they? All right, and then popping from the stack is not too hard. We're going to return the stack. We decrement it, and that's quite simple. We're just we take the top index, reducing that by 1. So now instead of pointing at the next spot on the stack, it's pointing at the previous one, which was the last one we pushed. That's the decrement there, and then we're just returning that value. And then peek. We're just looking at the top item, but we're not necessarily reducing the top pointer because we're not removing it from the stack. So that gives us just a very, very basic stack, which is actually getting quite close to all of the fundamental groundwork that we really need. Now there is one other interesting thing that we need, and that is we need to decide how our VM is going to execute instructions. You can design instructions a lot of different ways. If you look at the JVM, there are a whole lot of instructions, but every instruction, I believe, in the JVM is 1 byte. And there are a lot of other VMs that work that way. There's some where they might be multi-byte. I read a bunch of documentation around the Smalltalk VM, which is one of the original bytecode VMs. And depending on which variant you're looking at, you've got some potentially multi-byte opcodes. I'm just going to keep it really simple and go with a single byte opcode. What that means is, as our VM is executing code, at any given time, it takes 1 byte of information to tell the VM what to do next. In order to do that, we're going to need some way of loading code. And so for now, code is just a sequence of bytes. If I keep the idea that bytecode is a single byte opcode design, then I can just have my code as a regular uint8. In order to load that code, though, it needs to come from somewhere. I've done a couple of experiments where I read it from standard input or something like that, but I think it's probably, by and large, best to do this by reading it from a file. So that way we'll tell our VM to execute the code in a particular file. So in order to do that, we need a quick function that loads a file into an unsigned integer 8 array. So we'll just write that out real quick here. So did I get my... Yeah, I got standard IO already. Good. And let's see, because my bytecode might contain null bytes, I've experimented with using some non-null byte encodings. For example, if I need to have an instruction that pushes something onto the stack, maybe it's a number, and I want to push a 0 onto the stack, that means I'm going to either have to have a null byte literal in the actual bytecode, or I'm going to have to represent it some way. I've experimented with representing it as hex to make it really easy to write it by hand and stuff like that, but ultimately for efficiency, I'm likely to want to put raw data into my bytecode. So that means I'm going to have null bytes. So I have to treat everything a little bit more carefully. I can't just, for example, scanf my code in from the file, because it may contain null bytes, it may contain new lines, who knows what's going to be in there. So I'll need to do a couple little things to keep track of that. We're going to return a pointer to the data, and I need stats. And if I look at, let's see, I need to, no, not that one. Yeah, I need a couple of, so we'll include a couple more stuff so I can get stats off of this here. And as I said before, I'm not really trying to be very robust with this code yet. So I'm not going to do really crazy error checking. I'm just going to, if I fail to open the file, I'll just print out some usage statement. We'll define that later. And then, but if it's successful, then all I need to do is fstat, grab the file descriptor from my open file and store it in my stat struct. And then from there, I can just read in my data. Pointer, lock. I suppose I should size up something there just for perfection, but who cares? So I'm going to read the data once I know how big the file is and how many bytes it is. So I'm going to read it into my code pointer here, and then I'm reading it in terms of bytes and this many bytes, and from that descriptor. So that should read my code in from a file. That should work. Let's do a quick usage statement here. We'll do a exit code of 1, means you didn't ask me to run correctly. So then in here, for our main, we've got basically, we can read our code in using load file argv1, but we only want to run that if we got an argument, so I guess we'll do a little bit of alright, and maybe I'll spell that correctly, something like that. Alright, so cool. Yay, it works. Oh, and of course that was the error because I got a really simple usage statement. Maybe we should actually there we go. There, cannot open file foo. Good. We have our basic machinery. We have a way to represent fundamental data types with our object struct. Then we got stacks. But now we'll actually, let's make a stack for the VM. There are a lot of different VMs that are stack machines that work different ways. You might have multiple stacks. I know for sure that I intend to have at least 2 stacks. You know, and when C is compiled to machine code, usually you have one stack, and that single stack is used to pass values to functions during function calls, and then also used to store return pointers. And it's an interesting situation where, because there's a single stack that you're using for 2 purposes, it increases some complexity. You have to think about stack frames, and you get interesting vulnerabilities in C programs, like buffer overflows, where if you have a stack overflow, you could maybe change that return pointer. Makes it a little bit dangerous. So since I'm making an abstract VM, I can do whatever I want. I know for sure I'm going to want to have a data stack. Now we might end up making some more stacks later, I don't know for sure, but minimally we'll have a data stack. So data equals stack new, and just for really round numbers, we'll say we have 1,024 slots on our data stack. I don't know if that's a small number or a big number. You know, maybe after I write some actually useful program in this someday, I'll find out that it should be way bigger, but we'll just start with this for now. And then we need some way to represent the current instruction pointer. So we've got some space in memory, which is our code, our executable code. And we need some way to say where we are in that code. So we can do that with just another UAT pointer. We'll call that the instruction pointer, just like we would call it in a real CPU. So IP equals code will say we always start executing code at address 0, which is the start of the code pointer. And actually, right now, what this kind of makes our VM is kind of a Harvard architecture. In a Harvard architecture, you store code and data in different places, and so in this case, this code variable refers to some region in memory that is distinct from the place where we're planning to store data. eventually, like I hinted before, we're going to end up probably with some pointers and maybe some more collection type fundamental data types, especially if we end up with, say, arrays and lists. Those will have to get stored somewhere, and they'll probably be stored on the heap because I'm keeping this really simple. But anyway, that sets us up for being able to execute code. But what does executing code look like? There are a lot of different ways that people do this. For example, you might have a big switch statement where for each different opcode you have a different paragraph in your switch statement. Been reading a bunch of different approaches for doing that kind of thing, but what I've kind of settled on, at least for now, doing a little bit of sketching, is that I really want to have just use an array of function pointers. The point just being that I need to be able to equip my VM to be able to call the right functionality every time it reads a new instruction from the code. I've got my bytecode, which tells the VM what to do. Well, the VM has to actually be able to do it. So just to keep things somewhat simple here, I'll do a basic function prototype here. Oops. So an instruction type is going to be a function pointer. If you're not a C programmer or not used to function pointers, sometimes this is considered the deep arcane part of C. But basically what this says is an instruction type is a function pointer. That's what this parenthesized chunk refers to. And an instruction function returns a pointer to an unsigned 8-bit integer, and it takes as its arguments one of those 8-bit unsigned integer pointers and the address of a stack. Basically the point being that if I have any instruction in my VM is going to take two things in. It's going to take the current stack, which for now is just going to be the data stack, and then it's going to take in the current instruction pointer. It's going to carry out whatever that current instruction is, and then it's going to return the new instruction pointer. The reason I want to do that is that some instructions may change where the instruction pointer needs to be. If I have a jump or if I have a call instruction or something like that, it may change the location of the instruction pointer. More than that, even though each opcode is going to be a single byte, that doesn't mean that the next opcode is always 1 byte away. And that'll become more apparent in a minute. The reason is because of immediate values, and immediate value may not have a lot of meaning yet, but like I said, we'll get to an example of that real quick before being able to hit our objective for the first video. So we're going to define a type. Let's make sure this guy still compiles. Yes, I'm still typing things correctly. They're all spelled right. And because I'm using a single byte for my opcode, then I can represent all of the possible opcodes by having an array of 256 elements. So we're ranging an index from 0 to 255. So what this means, especially for those not function pointer comfortable, is that I have an array of function pointers. These are just locations that the VM can jump to for execution for each of the opcodes as they come in. Now, to be safe, what I want to do, I'm going to create my first opcode. So the first opcode is going to be something like this. We'll call it, let's call it instruction. Well, we can call it nop. So a nop is, and how did I define these? These things take in the current instruction pointer, and then they take a pointer to a stack. And so a nop is a no operation. It just means don't do anything and then go on to the next instruction. So that makes it really simple because every opcode is a single byte, and then this opcode is not going to take any arguments, obviously. In order to do a nop, all I have to do is say, go to the next instruction. So in that case, now I can take that ops array and I can say something like ops each slot equals an op-nop. So what this means now is that all opcodes in my VM are nops. Nothing actually does anything useful. And now I'm pretty much ready to make the most fundamental basic program that my VM might ever execute. We have to have an execution loop. This will be similar to like a main game loop or something like that if you've done interactive programming. Basically, we have a while loop, and we say in pseudocode it's while IP is not a halt instruction, right? Well, what is a halt instruction? Well, now I'm going to have to define that. I'll say, in my case, just to keep things easy, a halt instruction is an H. So any H, I'm going to make this prettier, there we go. Any H in the input stream, and H is a single byte, is going to represent a halt, and that tells the VM we're done executing, and so we're going to exit. And then for each instruction that we're going to execute, we're going to load the instruction at that IP is pointing to, and then we're going to call the associated function in our function table of ops. So that looks something like this. We know that each of those instructions is going to carry out some action and then return the new location for the instruction pointer, because each instruction itself knows how much space in code it's going to take. So the new IP equals the function pointer that is represented by the current byte. So I'm going to take the instruction pointer, dereference it, that gets me a character out of memory, and a byte. And then we're going to use that as an index into this table of function pointers. Currently they're all nops, but anyway, we're going to run this, sending it the current instruction pointer and the data stack. So something like that. So now what this does is we'll take that code value, the data we read from the file indicated on the command line, and then we're going to start at the beginning of it, and every time through this loop we're going to read an instruction, find the function pointer, call it with the current state of the VM, and then use the response from there to update the instruction pointer, and then loop again. So the most simple program we could write would be the program that halts right away. So this right here is a machine code program for my little VM. So we can hop back here. Uh-oh, we have an error. Makes integer from pointer without a cast. What did I mess up? Oops. That's right, because this should be a pointer. So we have to make sure we receive a pointer, add to it, and return a pointer. Hopefully I didn't mess any more up that way. So we can run halt.vm, and that's kind of what we would expect. We can at least see that, yes, it returned a 0. And the only way for our program to return a 0 is for it to make it here. So that means we successfully ran the most basic and simple program. But that's not very interesting. We probably want to set up some slightly more interesting ones. So let's add a couple more instructions. Let's do an instruction to push a character onto the stack. So remember at the top when we defined our object struct, we said that we can have signed and unsigned 8-bit integers. So actually, you know what? Just for convenience, I'm going to store this in a register in Emacs. So this will be push char. So if we're going to push a character, how's that going to work? Well, we're going to have some byte that represents the opcode for this operation, but then right after that we'll have a parameter. This is one of those few cases in a stack machine where we're not just going to operate on objects on the stack, we're also going to have a literal argument for this instruction. So it's a little bit more complicated than the op. We're going to need an object, so we'll just object O, And then O needs the object needs a type. Now we know we're pushing a character, so we'll just say the type is a character. It's very convenient using a char for this because I can just have little character mnemonics for each of my data types. That makes coding it pretty easy. I could just as well have some defines and have, like type char or something like that too, but this keeps it simple, and actually there's some fun advantages to doing it this way later anyway. And then, if you remember, we had this union right here. Well, if I'm creating a character, I'm going to say this is an unsigned 8-bit integer. So when we do, where did I put that? There it is. So we're just going to use the U8 value. We're going to make that the next byte in memory after the opcode for pushing a character. And when I write a program using this, you'll see what that means practically speaking. So what we really want is to dereference the next byte after the instruction pointer. All right, so we're going to take the instruction pointer, increment it by 1, and then dereference it with the star. And then now we have this object. So we can push that onto the stack. So stack push S O, and hopefully that will end up giving us the next object there. Should hopefully work. And then now there's a nuance here. Because this instruction takes an argument, we're going to end up needing to not just increment one location in memory for the next instruction, we have to skip the literal value. So we're going to do IP plus 2 in this case. So then down here somewhere, I'll just throw it in here for now, I might factor this out at some later point, but ops, I have to decide what is the bytecode for pushing a character. We'll call it C because that's easy to remember, and that's going to be op, what did I call that? Op push char. There we go. And then let's do one more instruction here, and we'll do emit. If you're not a fourth fan, emit is going to take a character off of the stack and it's going to print it out to the standard output stream. This just allows us to have some output and thus make a program that actually does something. So first we need the object that we're going to emit, and we'll consume it. So this is stack pop S. Right, so that's going to take the object on top of the stack and pop it off. Now we have a reference to that. Or actually we have a copy by value version of it. And then we need to actually print this guy out. So we'll just use put char. There we go. And then this instruction doesn't have any literal arguments, so it's a single byte, and then the next instruction should come immediately thereafter. So we just increment instruction pointer by 1. And then we need to give it an opcode. We'll give it an E. Should be something very much like that. So make sure, yay, we have no errors. And so now let's write a simple program. We'll call it hello.vm. So what do we want to do? I want to print hello world. So we're going to have hello world as our string. Of course, because it's a stack-based language and it's last in, first out, we'll just reverse the order of these. So we'll, what is that, rev? Yeah, so hello world, and then we'll add C. So what this means is we're going to push all of these characters onto the stack. So C bang means push a literal character, and the literal character is going to be an exclamation point. And then the next instruction says push a character, make it a D, push a character, make it an L, push a character, make it an R. We're going to end up with the characters for hello world sitting on the stack. And actually, as a little idiosyncrasy, we want a new line at the end so that we make a full and complete hello world program. But now we want to emit all of those characters out to standard output. We use the 2 instructions that we have so far. And so we've got, well, So we need 13. So we'll put 13 E's in there, and then we'll halt when we're done. So hopefully this makes some sense. What hello.vm does is it pushes a bunch of characters onto the stack, and then it emits them all, and then it halts. Obviously, this isn't the best way to do this program. We really should have loops, or maybe we should have some representation for strings. It shouldn't have to be written this way, but for now, our VM is so simple, it can really only do two things. It can push characters, and it can emit them out to the standard output. And it can halt. So we'll make that our program. So you can see halt.vm looks like that. Hello.vm looks like that. And in principle, if we're really lucky, and of course I'm doing this on recorded video, hopefully this will run hello VM. So hello VM prints out hello world, and then it exits. Should see our return code is 0. And so that gives us the essential shell for a bytecode VM. The guts of it are, we need some way to represent data, we need some way to represent a stack, and then some way to represent operations in our VM, and then the basic machinery to execute code. In later videos, we'll add some more instructions, some more opcodes, because obviously we need things to pop the stack, swap the objects on the stack, push numbers. Maybe we need things to jump to different places. We'll need some conditionals. We need the very fundamental operations that are required to make a useful stack machine. But in this video, I think we've put together a pretty good basic shell for what makes a bytecode VM. This can be enhanced fairly straightforwardly to do all of those different things. So in the next video, we'll probably get this to the point where we have some conditionals and jumps and things so that we can do very basic programs. In fact, I think my goal for this video was to do hello world. I think my goal for the next video will probably be to get to a point where we can do a factorial or something along those lines. So with that, I think I'm done with this so far. Hopefully next video will expand this further and we'll get closer to a point where we can make an assembler and then a compiler for high-level language, and then we can really start playing with some interesting things.